Welcome back to Bal Vigyan Bharati with Vilas Sarkar. This is the last session and last episode for fluid dynamics. There I will show you some problem and their solutions on the last segment of the chapter that I have taught in fluid dynamics, and that would be the last one, because in every segment I have shown some problems that was related to the subjects that I have taught. So this time I've taken some other methods of teaching. Earlier I was used to show you all the theories, and then after that at the end I used to show a number of problems. But I think that also I don't know, it's very much acceptable to the students, because I understand there are there are students who are very much interested in getting problems solved with the theory being taught immediately, so that clarity may come immediately on the theory, because some of the theories will be more relevant to understand with the examples. So that would be the best method of teaching, I suppose. So I adapted right now. So I taught you the theory, and consecutively I have shown you some example related to that theory immediately, so that conceptually the theories are very much understandable to the students who are new to the subjects. So I will try to do this way in further classes, further subjects also. So let me start this last segment with few many problems, and that would be the last on this subject. And kindly review and give your feedback. If any case anything goes wrong, or anything you are not able to understand, or anything is not acceptable as per your understanding, so we can talk on this, and specifically if you want to discuss about some problem or any part of the subject that I taught almost around 32 odds episodes. So you can anytime can come back and comment on the comment sections. I would love to have those feedbacks about the classes, about my way of teaching and all that. Anything. We don't bother about the questions or your feedback. I will take all as a positive feedback from you, so that I can at least make myself improved. I want to grow. I want to, because this is my personal experience I'm doing. I'm never taught. I'm never means in that this kind of you can say professionally. I never been into the teaching profession. So this is my raw experience, and whatever I'm doing with my own ideas. So it will be always be better if I can get your review, your guidelines, whichever way it will come. I will take it positively. I don't mind whatever things will come, whether it is negative or positive, whatever way. I will take all this to improve my skills, and I can deliver better to you. So thank you. On this note, I'll move on to the subject, and this is the first of the problem on the last segment of the theory. It says a square metal a square metal plate of area 2 meters square is moving horizontally at a speed of 2 meter per second by applying horizontal tangential force over the free surface of a liquid if the depth of the liquid is 4 meter and a liquid at the bottom is stationary, then the tangential force needed to move the plate is how much? Given coefficient of viscosity is 10 to the power minus 3 decapoise. CSE. Okay. So let me read it out again. A square plate of area, let's say this is a square plate of area, okay, 2 meter square, so that means this is root 2, this is root 2, and the area is 2 meters square, okay, is moving horizontally at a speed of 2 meter per second. So this is having a speed of 2 meter per second. By applying horizontal tangential force, so there is a force which is being acted this way tangentially. It is about how much horizontal tangential force free on the surface. So the force is not said how much it is, okay. Free surface on the liquid. Apply on the horizontal tangential force over the free surface of the liquid. So there a force is acting, this force is being transmitted here and it is giving a tangential force on the liquid. So we can think of another plate which is just beneath it. And in between some liquid is there, means you can think of liquid, it is being bounded by some means, so that we can think of a liquid inside it, okay. You can think of a liquid inside it. It is fine, and the layer just adjacent to this plate having is getting a tangential force on the surface, the free surface, okay. Okay, fine. Up to this, if the depth of the liquid is 4, so this depth is 4 meter, okay, between the plate. and the liquid at the bottom is stationary, so this is not moving. This V is equal to 0. This is at rest. Okay, fine. So this is the first part of the theory where we are discussing about two metal plates, two plates. One is stationary, one is moving, and it is sliding on the liquid. It's interrupt in between that, so it is getting that velocity on the top. Fine, and stationary. Then the tangential force needed to move the plate is how much? So what is the tangential force? It is because on the other hand, it will get a viscous force on the opposite end. So what is the force needed to move this plate? So the layer will give a opposite direction. This is a viscous force. That liquid layer is in contact with the plate, give a viscous force on the opposite side. So what would be the force needed to move the plate? So to move the plate, the least force, the tangential force, must be equal to the force of resistance. So just if it is able to overcome that force, it is dragging on the opposite side, it will start moving. Whether it will get accelerated or not, it will start moving, maybe in the constant velocity. The net force is 0. If this force are equal, so it will start moving. Okay, so this is the condition when the force is balanced and it is start moving. So what is the force Ft? So the Ft is equal to Fv. So Fv is equal to how much? Minus eta and what else? A dV by dy. Okay, or if you can say the velocity gradient v2 minus v1 divided by the distance, the delta y means the distance between the layers. So I am talking about this layer. So this is the reference frame. We say this, there is the reference frame you can think of. So this is at 0 and this is at 4. So it will be 4 then. All are in SI unit, so no need of. So this is getting velocity v2. This is at rest. So this v2 is equal to 2 meter per second and v1 is equal to 0. A cross section area, that you know, 2 meters square. This is in SI. What is eta here? Dynamic viscosity. Now this is 10 to the power minus 3 decapoise. Now eta in decapoise means eta, the unit we know, that is equal to m L to the power minus 1 T to the power minus 1. In SI, this gives kg meter into second. This is equal to 1 decapoise. This value is equal to 1 decapoise. Okay, kg meter per second is giving the 1 decapoise. It's equivalent. Now this is given as 10 to the power 3 decapoise. That means this will be the units 10 to the power 3 decapoise, 10 to the power minus 3 kg meter into second. Understand? So that's why I put. So if I put all this value, I need some space. I will rub it up. You understand the schematic arrangement. So now I'll put this value. Now Fv is equal to eta is minus 10 to the power 3 decapoise. I will talk about the units parallelly. So what I will take kg meter per second, because this is your decapoise. 10 to the power minus 3 decapoise, this is your decapoise. 1 kg per meter per second is equal to 1 decapoise. Okay. Area 2 meter square into v2 minus v1, 2 meter per second, it is 0 meter. So ultimately 2 meter per second. Okay, into divided by your y distance 4, that is in meter. So if I calculate all this, so I am going along with the unit so that there will be no confusion at the end. What is the unit? 2 into, so I am keeping all the numerical here. So 2 into 2 4, that will again 4 And now we'll start with the, so that is kg. In the top is kg. This is kg, meter cube. So this will be meter cube. Okay, this meter into second, that will come down, and meter again. So meter cube again, meter into meter, sorry, meter square, not meter cube. This is meter, there is no meter again. So meter square, this meter in this meter again together is meter square, and there is second here, so second square. Understand? All units came here. And now this is equal to 4 cancelled out. There is no units, no further numerical. 10 to the power minus 3, and here it is kg, meter square, meter cube. It will cancel. Only 1 meter will remain. Okay, so this is meter per second square. So what is this meter per second, kg meter per second square? Meter per second square is the unit of acceleration, mass into acceleration, that is your force in SI, it is Newton, so 10 to the power minus 3 Newton. So this is the answer. What is the force needed to move the plate? So force needed to move the plate is Fv equivalent Ft. So Ft, only thing is it will be numerically equal, means if I write modulus value of Fv and Fb are equal, but what is the exact value? Fv and Ft has to be in the opposite direction to balance it. So Ft must be minus of Fv. Now Fv is equal to, minus will come along with this. This is minus, so minus of minus is equal to plus. This is equal to minus 10 to the power minus 3 Newton. So that is 10 to the power 3 Newton. So that means this having the direction of motion on the right side. Okay, which way the velocity is needed, so that the minimum force which is needed to move the plate on the top, so that it can give a motion to the liquid layer adjacent to that, it is 10 to the power minus 3 Newton. Understand? Okay. We'll move to the second problem. Uniform speed of 2 centimeter diameter ball is 20 centimeter per second in a viscous liquid. Then the speed of 1 centimeter diameter ball in the same liquid is how much? Okay, fine. So uniform speed of 2 centimeter diameter ball, it's a ball moving in a viscous liquid. So from this two term we can definitely understand when you are studying this subject, so immediately it is very easy to catch the problem which is related to which theory. Now to catch when you are, we will solve a different kind of problem in a same question paper, there may be a different kind of thing and you may confuse. So it is very much essential to correlate and understand what is it. Now, uniform speed of a ball in a viscous medium. Now, when that viscous liquid will come, you definitely can come to a conclusion. This is about your fluid dynamics, because in dynamics, when you are talking about viscous, only the things you are talking about, because in any other motion you will not talk about the viscous thing. Viscous is coming when you are in fluid dynamics. So fluid dynamics, this part is very essential to understand viscous. And when we are talking about ball, you just correlate with the Stokes law. Okay, and if it is uniform, that means the part of Stokes law where we have reached to the terminal velocity, then only it will be a uniform velocity. Before than that, that motion is accelerated motion, because whatever I shown you, the viscous fluid, the velocity against that time, which is exponential, then after it is become a uniform velocity, but prior to that it is being accelerated. How I am saying, v against t, this is v against t, this is the delta v by delta t. What is this? It is not same, but in this case v, if I take, it is same. So delta v is equal to 0 here. So delta v, now there is no velocity change, the uniform velocity. So this part of this is called acceleration, because what is the slope? This upon this, your acceleration delta v by delta t. So unless you are reaching there, that means at terminal velocity, you won't get uniform velocity. So this uniform velocity is nothing but your terminal velocity. Understand? So if you understand this, now the next thing is very easy, because for this we have a definite formula. So what is that? That Vt, if you have remember, if you don't remember even all this part, the only thing is that you remember it is proportionate to r square. So you take it as constant, because this is the problem related to the comparison, where you can use your skill not to remember all the part, rather how the Vt is related to r. It is related to in square form. Okay, fine. So here nothing is varying, only the diameter is varying. So that r again is just diameter by 2. So then you can understand, if I are with the respect of r, we can with the respect of d will be in same way. So this you can say another constant into d square, because this will again a constant, this will come as a 4. So then it will be d. Understand? So in the next part, this is, so ultimately you need not to remember for this sum particularly, whereas if you want to remember, so Vt is equal to 2, what else, 9 eta, what was there, sigma minus rho is there, into r square is there, into g was there. Am I missing anything? This was the formula. 2 by 9 eta is there, rho minus rho, r square. So you can understand this, all these are constant. So you can take this at your will in any constant. If I put g here, so if of your will, this is a constant, because this part for a particular problem, rho and g, rho and sigma will not vary. Okay, and only the variation is rho. So here Vt is related, so this is your equation 1. So for first case, when the diameter is 2 centimeter, you are getting velocity, uniform velocity, so Vt. So Vt for 20, you are getting k2 into 2 square. And what is when diameter, so I am getting Vt, let's say, when k2 is the same, and this is 1 square. So if it is the equation, you can take, this is first of the form where your diameter is 2, and second case your diameter is 1. So you can divide it, or else K2 if I compare, it is 20 square, 20 by 2 square is equal to Vt by 1 square, it is 1. So Vt is equal to how much from there? 20 by 4, that is equal to 5. So your terminal velocity for 1 centimeter ball will be 5 centimeter, no? These are in centimeter, this is centimeter, this is centimeter, yes, centimeter per second. It will be your answer. So for this particular of problem, you need not to remember all this, but whereas if you remember this will help you solving other kind of problem where these are available, this information are given, okay, or you can calculate even. So you need to have remember this equation by heart. So you cannot derive it, and it will take time. You can derive it, but it will take time. If practice at home, more you practice deriving this, it will give you more confidence to remember it. Don't remember without deriving yourself by your own. So you just understand when you derive it, you will face some problems, so you will solve those problems. So it is very much essential to derive your own any formula, any unit of measurement, whatever is there, you just try to write it down and do your own, so that you can remember by heart. If you want to just remembering by reading it, it will be very difficult to remember, because at the time of requirement you won't find your memory is working, because that time it will be very crucial, and your mind will be puzzled with so many of thoughts. So you cannot remember a particular this kind of equation. So you better you practice, you do it your own self, you just derive it your own, and you can remember it very well. Okay, so this is my suggestion. So this is the answer for this question. Now we'll move to the problem number 3. Okay. Problem number 3 says two small spherical metal balls having equal masses are made from material of densities rho 1 and rho 2, whereas rho 2 is given as 8 times of rho 1. Okay, oh sorry, that's reverse. Whereas it is given rho 1 is 8 times of rho 2. Fine. And have radii of 1 millimeter and 2 millimeter respectively. They are made to fall. They are made to fall vertically from rest in a viscous medium, in a viscous medium whose coefficient of viscosity equals eta and whose density is 0.1 rho 2. Find the ratio of their terminal velocities. Okay, find the ratio of the terminal velocities. Fine. Okay, so this may be the last problem for this episode. I will take another episode which is going long, so I will not stretch it too far. So in the next episode definitely I will finish this chapter. So for this question, let me read it out again. The two small spherical metal balls having equal masses. So if I assume the two metal balls are of M1, M2, so that M1 and M2 are equal, and that we can take it as M. Made up of material of densities, this having density rho 1, this having density rho 2, and the relation is rho 1 is 8 of rho 2. I am just writing the information in one place so that we can go ahead. Is equal to, this both are equal to M, and this is rho 1, rho 2, these are the densities. And I have radii of 1, this is having 1 millimeter, this is 2 millimeter. Okay, now right now I am not converting into the CGS because these units are given, only one unit is there, 1 millimeter and 2 millimeter, that can be converted into centimeter. Okay, so I will do it later if it is needed. They are made to fall vertically from the rest in the viscous medium whose coefficient, the medium, this is the balls, this is this metal balls description, and the media through which it is falling having viscosity of eta media, this I am taking as eta, the fluid viscosity, and the density is given as 0.1 rho 2, that is the density of the metal ball, second metal ball with respect to that. And what is the so if I can say, I take the terminal velocity for first ball, it is something there only which density is also different, so we can take any constant, and the relation of densities is this into r square. These are other things we can take constant, and the previous case we have taken all this constant, but here it is differing as because densities, there are two different balls, so the densities will be different, the sigma will be different for different ball, and with respect to the fluid through which it is moving. So we can say that the terminal velocity depends on the constant into this part. So for first ball it is sigma is how much? It is rho 1. Instead of sigma I will put rho 1, and whereas this is nothing but the fluid having density 0.1 into rho 2. I am writing like that. And for first ball the radius is, I am not converting into centimeter because if I want to make ratio of two densities, because you need a ratio, so while you are doing ratio, the conversion also will same for both the case, so I need not to be worried about. Instead of that I put the values directly. For second ball, if it is V2, the terminal velocity, the constant will be same, and instead of rho 1 it will be rho 2, and the other things will remain same, only the radius will be 2 square. I am putting in same unit, because at the end I will do the ratio, because whatever conversion will take to bring it in centimeter, that the same conversion will be at here. I mean, while I'll do ratio, it will be nullified. So I'll do ratio of these two. Okay, so this will be the equation. So this kk will go up. So what else? Row 1 is how much? 8 of row 2. You can put it 8 of row 2 minus 0.1 row 2, and 1 is nothing but 1. Here row 2 is there, minus 0.1 row 2, and 2 square means 4 will come here. So V1 by V2, the ratio I need. So row 2, everywhere row 2 can be cancelled out, taking it common. So what else will remain here is 8 minus 0.1, that means 7.9 will come here, and it is 4 into 1 minus 0.1, that means 0.9 will come here, isn't it? So this is 7.9, 4 9 is a 36. So if I remove it, I will get something 79 by 36. This will be the ratio of their velocities. It cannot be reduced for the, suppose 3 to 0, no factor is common in between these two, so I cannot reduce it further. So the velocity ratio will be 79 by 36. This will be the answer. Understood? So here I will end this session, and next session I will move from the problem number 4 onwards. I may take another class to finish this off, and then after I will move to new subject of mathematics. So thank you for now.